Welcome, this is Scaduto speaking, and this is part 4 of a 4-part series on equivariant singular instanton homology. Everything here is joint work with Ali Daemi, and let me give my final thanks to the organizers of this conference. In this talk, we'll explore some further applications of the theory. While the results depend on the previous parts of the series, much of the talk will be an exposition of the applications, and should be accessible to those who are just joining. So let's get to the first application. This application has to do with knotted surfaces in 4 manifolds and the existence of certain SU2 representations. A classical result, which follows from the loop theorem of Papakyriakopoulos, says that if K is a knot in the 3-sphere, then the fundamental group of its complement is infinite cyclic if and only if K is the unknot. Note that the abelianization of the fundamental group of a knot complement is always isomorphic to the integers. So the theorem can be restated as saying that the knot group is not abelian if and only if K is non-trivial. This result has the following upgrade due to Kronheimer and Rovka. If K is a non-trivial knot, then not only is its knot group non-abelian, in fact there exists a non-abelian homomorphism from the knot group to SU2. Motivated by this discussion, we can ask the following analog in 4 dimensions. Given an embedded 2-sphere F inside the 4-sphere, which is sometimes called a 2-knot, if the fundamental group of its complement is infinite cyclic, is this 2-sphere unknotted? So if this question is asked in the smooth category, then this is an open problem, as far as I know. On the other hand, if you ask this question in the topological, locally flat category, then the answer is in fact yes, which is due to the work of Friedman. We can go on to ask a similar question for knotted tori in S1 cross S3. Suppose now that F is a 2 torus which is embedded in S1 cross S3. And suppose further that the map induced on first homology by inclusion is surjective. Then, if the fundamental group of its complement is isomorphic to Z plus C, is F equivalent to S1 cross an unknot? I'll remark here that the condition on the fundamental group is equivalent to it being abelian. One way knotted tori in S1 cross S3 arise is by the following construction. So let's take a concordance S inside of an interval across the 3-sphere, and suppose it goes from K to itself. Then we can glue this concordance up. So here note that a concordance is topologically an annulus, and if you glue it up, then you get a torus. So I've indicated this construction in the following diagrams. On the left we have the concordance S from the knot K to itself. On the right we've glued everything up and obtained the torus S hat inside of S1 cross S3. In this setting we have the following result. Suppose S is a smooth concordance from a knot K to itself. Then if the signature of K is non-zero, there exists a non-abelian homomorphism from the fundamental group of the complement into SU2. From this, we obtain that the fundamental group of the complement of the 2 torus S hat is non-abelian. This result follows from a more general version, which I'll now describe. First, we make a definition which both generalizes the notion of smooth concordance of knots and also the notion of homology cobordism of integer homology 3-spheres. So suppose K and K prime are knots in integer homology 3-spheres y and y prime, respectively. Then a homology concordance is a cobordism of pairs Ws, where W is an integer homology cobordism from Y to Y prime, and S is an embedded annulus cobordism from K to K prime. Everything here is in the smooth category. So just like in the settings of concordance and homology cobordism, the pairs YK up to homology concordance form an abelian group. And we call this the homology concordance group. We have the following homomorphisms. The first top homomorphism is from the smooth not concordance group to the homology concordance group. And this just maps a knot in the 3-sphere to itself. The second homomorphism on the bottom is from the homology cobordism group of integer homology 3 spheres to the homology concordance group. This homomorphism sends an integer homology 3-sphere Y to the pair Y with an unknot, where the unknot is in a 4-ball embedded in Y. To state the following result, we also need the Froyshov invariant from instanton theory. This is called H and is a homomorphism from the homology cobordism group to the integers, defined by Froyshov. Now, if you haven't seen this, you might have seen the Hegardt-Floor D invariant. Conjecturally, H is 1/2 the D invariant. So that's the type of invariant that's appearing here. Now we can state the following theorem, which is a generalization of the previous theorem. Suppose Ws is a homology concordance from Yk to Y prime K prime, such that K is null homotopic inside Y. Suppose further that the Froyshov invariant of Y is not equal to 1/8 of the knot signature of K inside of Y. Then there exists a traceless representation from the fundamental group of the complement of the surface into SU2, extending non-abelian traceless representations of the knot groups of K and K prime. In particular, the fundamental group of the surface complement is non-abelian. Here, traceless has the following meaning. The surface S has a unit disk normal bundle inside of W, and the boundary of this normal bundle is a circle bundle over S. The representation being traceless means that the circle fibers of this normal bundle are sent to traceless elements of SU2. Now I'd like to say a few words about where this result comes from. Recall from the previous talks that to a knot K in the 3-sphere, we associated what we called an S complex, C tilde of K delta, which is a certain kind of chain complex over the Laurent polynomial ring in 2 variables. Now, given any algebra over this ring, script S, we can do a base change and obtain an S complex C tilde K delta S simply by tensoring. We should also assume that the algebra S is an integral domain. Now I should remark that the constructions in the previous talks work more generally for knots in integer homology 3 spheres Yk, not just knots in the 3-sphere. So for any choice of algebra S, which is an integral domain, over the Laurent polynomial ring in 2 variables, we have an S complex associated to any knot in an integer homology 3-sphere. And from this S complex, we can algebraically define a Froyshov invariant. See part 3 for the construction. We call this invariant HS, and it's a homomorphism from the homology concordance group to the integers. We call it HS because in general it depends on the choice of the algebra S. Furthermore, recall that there's extra structure on this S complex. This has to do with the Z cross R bigrading and the filtration induced by the R grading. From this extra structure, we can extract a homology concordance invariant called gamma. See also Part 3 for its construction. So for this, we have to assume that S is of a particular form. It's some ring R adjoining the variable u plus or minus 1, where R is an algebra over the Laurent polynomial ring and the variable t. Now let's look at some important properties of gamma which are relevant to the above results. The first property says that gamma of I is finite if and only if I is less than or equal to the associated Froyshov invariant, and this property was discussed in Part 3. The second property is the following. Suppose Ws is a cobordism of pairs from yk to y'k', such that its first homology is 0, the homology class of S is divisible by 4, and the double-branched cover of W with respect to S is negative definite. Then we have the following inequality. Here, tau is an invariant of the cobordism Ws, which is a non-negative real number. The important property of tau for us is that it's positive unless there exists a traceless representation from the fundamental group of the surface complement to SU2, which extends irreducible traceless representations of the knot groups. It follows from this second property that if gamma yk is not equal to gamma for the unknot, then there exists a representation as described above. However, from the first property, for gamma yk to not be equal to gamma of the unknot, it suffices to show that the Froyshov invariant is non-zero. Therefore, we obtain the following. If the Froyshov invariant of yk with respect to the coefficient ring R is non-zero, then there exists a representation as described above for Ws. Now, the first theorem I stated follows by taking the coefficient ring R to be the Laurent polynomial ring in the variable t. For in this case, we have a theorem, first stated in Part 3, that the Froyshov invariant is exactly equal to minus 1/2 the signature of the knot. The second theorem we stated follows from a generalization of that result for knots in integer homology 3 spheres. The result is as follows. Let R be this Laurent polynomial ring in the variable t, and K a null homotopic knot in an integer homology 3 sphere Y. Then the Froyshov invariant that we define for yk is equal to 4 times the Froyshov invariant of the integer homology 3 sphere Y minus 1/2 the knot signature. We carry along the coefficient ring R in our notation because it's very important. This result doesn't hold for any choice of R. In fact, if we take R to be the integers, then the invariant we get, which we just call H, behaves very differently. This was already discussed a bit in Part 3. There it was pointed out that H provides a lower bound for the unoriented four-ball genus, and in fact agrees with the lowercase upsilon invariant of a knot minus 1/2 the signature for a large family of knots. So this includes quasi-alternating knots and torus knots. But if we take the coefficient ring R equals Z, we can still apply all of the above arguments. In this case, we get a variant of the first theorem we stated. So if S is a self-concordance from a knot K to itself, and instead of the signature being non-zero, this invariant H is non-zero, then still there exists a non-abelian traceless representation from the fundamental group of the complement of the surface to SU2. Now let's move on to a second application. This application has to do with the irreducible instanton homology of torus knots. So recall from part 2 that the irreducible instanton homology of a knot, I star of k, is a Z-mod 4 graded abelian group which categorifies the signature over 2. It's a direct analog of Floer's original Z-mod 8 graded instanton homology for homology 3 spheres. At this point, I'd like to remark that this theory works for knots in integer homology 3 spheres, just like above. And in this generality, we have the following relation. The Euler characteristic of the irreducible instanton homology of yk is equal to 4 times the Casson invariant of y plus 1/2 the knot signature. And this, again, is essentially due to the work of Chris Herald. For what follows, we'll stick to knots in the 3 sphere. In this case, the chain complex for I star of k is generated by the character variety of irreducible traceless SU2 representations for the knot, possibly having to use a perturbation. Now let T-P-Q be a torus knot, where P and Q are positive coprime integers. In this case, it turns out we don't need a perturbation, and you can count the number of elements in this irreducible character variety. It's exactly minus 1/2 the signature. In particular, the signature is negative. Since minus 1/2 the signature matches the Euler characteristic of I star of TPQ up to a sign, we can conclude that the chain complex for the irreducible instanton homology has no differential. More precisely, we may conclude that I star of TPQ is isomorphic to the free abelian group of rank minus the signature over 2. But what about the Z-mod 4 graded isomorphism type of this group? In the above argument, the Euler characteristic of I star is exactly minus the size of the generating set of the chain complex. This lets us conclude that I star of k is supported in odd gradings. But how much of it is supported in grading 1 mod 4, and how much in grading 3 mod 4? Poudel and Saveliev conjectured that the support is roughly evenly split between gradings 1 mod 4 and 3 mod 4. So we proved their conjecture, which is made more precise here. In particular, I star of TPQ is completely determined by the signature as a Z-mod 4 graded abelian group. Now I'd like to sketch the proof of this result, which uses ideas from the previous parts of the series, and in particular the equivariant structure of the theory, even though the statement is really independent from this structure. First, it suffices to prove the result in the setting of local coefficients. This is because we showed that the differential is equal to 0, and therefore the statement is really about the chain complex, which is freely generated. Next, we have inequalities that relate the ranks of the irreducible instanton homology to the associated Froyshov invariant in this setting. These inequalities follow from the theory of S complexes algebraically, and are not particular to instanton homology or the choice of coefficient ring here. What is special about this coefficient ring is the theorem, which we've already used once above, that in this setting, the Froyshov invariant is exactly minus 1/2 the signature. This gives us lower bounds on the ranks of the irreducible instanton homology in terms of the signature. But we already have that the total rank of the irreducible instanton homology is exactly minus 1/2 the signature. So combining these inequalities, we obtain the result. I should remark that some previous progress was made on this conjecture by Nima Anvari. His approach was to compute the gradings of the generators of the chain complex directly. This involves computing some equivariant row invariants. So you can see that our approach here is very different. Well, that does it for this talk and concludes our 4-part series. Thanks everyone for listening.